Welcome to the Space Telescope Public Lecture Series. Tonight's talk, How Dark is Space? By Dr. Tod Lauer of NSF's Noir Lab. I'm your host, Dr. Frank Summers of the Office of Public Outreach here at the Space Telescope Science Institute. And I really always make sure I thank this amazing tech team, Thomas Marufu and Grant Justice, who take this and get it out to you. I also remind you that the Space Telescope Public Lecture Series will be online only until further notice. Our upcoming talks. We're going to have a talk on November 2nd, but I haven't exactly pinned down who it's going to be, and then, of course, what they're going to be talking about. But don't worry, I always make it through. I got a whole bunch of people. I just got to pin it down to just one of them for that. So November 2nd, there will be a talk, and we'll find out soon about who that's going to be. On December 7th, we will have the James Webb Space Telescope Countdown to Launch. That speaker is also to be announced, but that's not my problem. That's somebody else who has to choose who's going to tell you all about this amazing, the James Webb Space Telescope mission as it's going to launch in December. More about that in just a second. In January, on January 4th, Maria Montesquiles will be talking about galaxy clusters, all right? And if you want to know more about these talks, you can go to our website, www.stsci.edu/public-lectures, or you can just go to your favorite search engine, type in Hubble Public Lecture Series, and you will find this page. On this page, on the left-hand side, you can find links to our webcasts, both on YouTube and our webcast archive from the Space Telescope Science Institute. On the right, you can find our sign up for the email. Just simply enter your address, hit subscribe, and you will be on our email list. Also on the website, we have all of the upcoming lectures. And if you click on one of those lectures, you will get the information about that lecture, the full abstract of the talk, as well as, after it's been recorded, links to the STSCI webcast, as well as the link to it on YouTube. In terms of email, well, as I said, the announcements, it's easiest just to sign up at the website. You can also subscribe to our YouTube channel. That is youtube.com Hubble Space Telescope, all one word, Hubble Space Telescope. When you subscribe, you will get notices of our new videos, as well as reminders of these live events. Finally, if you have comments or questions, you can send them to the email address publiclecture@stsci.edu. If you would like to follow us on social media for the Hubble Space Telescope, for the James Webb Space Telescope, and just STS Space Telescope Science Institute in general, we have Facebook, we have Twitter, we have YouTube, we have Instagram, and you can follow us at the tags there. Myself, I do a tiny bit of social media on Facebook and Twitter. Actually, a lot of it is all about just telling people about the public lecture series. Now, our news from the universe for October 2021. And the top story tonight is the James Webb Space Telescope. Save the date, because we had a wonderful announcement from NASA this month that the James Webb Space Telescope had completed its rigorous testing regimen, and also that Arianespace had a successful launch in July. Those two things, the completion of testing and the Arianespace successful launch, they were allowed them to set a target launch date for the James Webb Space Telescope, and that date is December 18th, 2021, which is, of course, why we're doing the Countdown to Launch talk in December. The James Webb Space Telescope is currently in shipment to the launch site, and that launch site is the spaceport in French Guiana. This is the European spaceport, where you can see it's just this amazing facility. This is a gorgeous image I found on their website. And in the front of this image is where they launched the Ariane 5 rockets. And Jadwist, he will be going up in an Ariane 5 rocket. And it also shows you why in this previous picture, the James Webb Space Telescope is folded up like this, because it needs to be folded up in order to fit in the top of that Ariane 5 rocket. Then after launch, it will have its unfolding, and that will be an amazing stuff, and you'll hear all about that in December. So we hope we're going to have some really, really happy holidays with both the launch and the deployment of the James Webb Space Telescope. Our second story: what's the matter with galaxy NGC 1052-DF2, which, by the way, I'm just going to call DF2 from now on. But I'm not going to start talking about DF2 right now. I'm going to first start talking about large galaxies with this example, the Sombrero Galaxy. Now, these large galaxies, they contain matter, all right? And when you look at them, you can say, oh, well, there's stuff that shines. We'll call this luminous matter, right? And when I say luminous matter, it's not just stuff that you can see with the eye in the optical, but it's also stuff that shines in infrared and ultraviolet and X-rays and gamma rays and all the wavelengths of the electromagnetic spectrum. So luminous matter is anything that shines, okay? And you can add up all the matter that you see that is luminous. You can also get an estimate of the mass in the galaxy using dynamics, okay? We'll call this dynamical matter. So for example, in this disk here, the stars are spinning, okay? They're rotating around in the disk. And the motion of its rotation, the speed of its rotation, it tells you how much matter is producing that rotation, right? So the dynamics of the stars can give you an estimate of the mass in the galaxy. Now, for most large galaxies, what we find is that the dynamical matter, the matter you get, from the motions, is much, much greater than the luminous matter, okay? Up to a factor of 10. And that means there's some non-luminous matter. And non-luminous, well, we'll just call that dark. So there is dark matter in these large galaxies. Up to 90% of the mass of these galaxies is dark matter. So that's the normal thing. It's kind of weird, but actually it's, for us in astronomy, that's the normal. Now, the weird thing is a galaxy like DF2. Now, this galaxy is, wow, that's really a puffball galaxy, because when you look at this image, you're actually looking through the galaxy, right? And you can see lots of other galaxies straight through this galaxy. I mean, it's really just, stars in this big puffy cotton ball type shape, but it's not very dense. It's a low density galaxy that you can see straight through. And some previous work on this galaxy had shown that it had very little or no dark matter. And there were competing groups that said, yes, it does, no, it doesn't, yes, it does, no, it doesn't, which is the way that science works, right? And in order to really settle this question, they needed an accurate distance. Because if this galaxy is further away, then it's bigger, okay, and would be more massive, right? And that would make the dark matter a problem. But if it's closer in, if it's closer to us, then it's smaller, and it's really not that much of a problem, okay? So what are they going to do? Well, you're going to call Hubble. And Hubble can see the individual stars in this galaxy. And this pullout, what you're supposed to notice are all those little red dots, okay? Those red dots are red giant stars. And there is a method called the tip of the red giant branch, and where the red giant stars reach a maximum brightness. And from that maximum brightness, you can accurately measure the distance to this galaxy. And that's what they did with DF2. The result was that the distance was actually larger than previously thought, pushing it further away, making the galaxy bigger, and making the problem with the dark matter even more problematic. There is a maximum of about a few percent dark matter in this galaxy. That is strange. So the questions we then ask are, well, how can a galaxy this large form without any dark matter, or very little dark matter in it, Right? We don't understand a formation scenario because usually the dark matter serves as the gravitational seed that pulls everything in to form the very large galaxies. Well, this is a sort of a dwarf galaxy level one. It's about 1 billion stars, whereas our Milky Way galaxy is like 200 billion stars. But those billion stars are spread out over a volume similar to the size or even larger than the size of our Milky Way galaxy. So this is a strange galaxy in multiple ways. Furthermore, when you find one object of this type, you always have to ask, well, are there others? And the main research group that announced this discovery says they already have one more, which is a similar galaxy to this. It's DF4. And they thought that they were close together in the same group. They actually turned out to be a bit farther apart than they thought. But they're going to study to find if they can find a class of these galaxies, what environments they live in, and use that to help understand how these galaxies without much dark matter could have formed. Stay tuned. Now, our speaker tonight is coming to us as a very special guest. Tod has a wonderful reputation amongst astronomers. He's just a brilliant speaker, so I know you're really going to enjoy him. He works at the NSF's National Optical and Infrared Astronomy Research Laboratory in Tucson, Arizona. He got his degrees from Caltech for his bachelor's and his PhD from University of California, Santa Cruz. He also worked at Princeton before joining the Noir Lab, and he has a wonderful history with the Hubble Space Telescope. He was part of the original wide field planetary camera team, and he's worked on things like black holes, galactic structure, stellar populations, and large scale structure. Recently, he joined the New Horizons team for what he's going to tell you about tonight. And I won't step on his things. And I would just finish with early in his career, he received the NASA Exceptional Science Achievement Award for his work on Wide Field Planetary Camera 1. So Tod, will you turn on your video and such and share your screen?
I will share my screen. Okay, let's
all right.
see.
Ladies and gentlemen, the eminent Tod Lauer.
All right. The eminent Tod Lauer needs to find the share button. There it is. Okay, goody. Let's see. Okay, and there. Okay, thank you, Frank, for that wonderful introduction. So I'm going to talk about how dark is space, and why not start with this wonderful graphic by this French surrealistic graphic illustrator, Guy Belot, who does these things for magazines, newspapers, what have you. And the concept that he has here is very simple. You have a couple astronomers looking out the dark slit of an observatory, pitch black, but wait, there are shadows there. There's light coming from the black space. And that's what I'm going to talk about. Is there light coming from empty space? And if there is, what do we learn from that? How do we know about it? How do we measure it? And what do we learn from it? So the first question that we can take up is, so why is it dark at night? And your first reaction is like, well, I think it has something to do with the sun going down. I need an astronomer to tell me this, But yeah, so the sun goes down and it gets dark at night. But why isn't there light at night? There's a lot of things there. Here's a picture over the Antarctic, way at the South Pole, which is one of the darkest places on Earth. And there's the Milky Way, and you can see a couple of our little satellite galaxies. The Magellanic Clouds are there in the upper left of the screen, and the image is peppered with stars and enough light, if you will, that with a long exposure of the camera, you can see, the South Pole even at night. So there is light coming from space, but it's dark. And I say, okay, well, sure, there's stars there. We're looking at 400 billion suns in the Milky Way galaxy right there in front of us. But, you have to be a dark place to see it. A little bit of city light will push away those 400 billion suns. So you say, well, they're far away and they're not that bright, and that's why it's dark. But if I put a galaxy behind this, it'll be brighter. If I put another galaxy behind it, it would be brighter still. If I piled it up, it would be extremely bright. And in fact, if you look right into the heart of the Milky Way, you see stars spread like dust. There's billions of stars on top of each other. In this image, you really can't separate one from the other. But it's still very, very faint. And this was something that came up, an old discussion from a gentleman named Olber. It's called Olber's paradox. If you looked out at the universe at night, and eventually, if it were infinite, you would hit another star. Stars upon stars, no matter how far you look. And then you say, well, they get fainter when they're further away, but there's more when you get further away, and it perfectly balances it. And the night sky should be as bright as the surface of the sun. And so the question, why is it dark as night, actually has this subtlety, and it says something about the universe. And if you looked at it and said, well, there's not that much stuff out there, then you've made a profound conclusion, which is correct. No need to take a fancy course in astronomy. You say it's dark at night, it means there's not that much stuff out there. The universe is finite. In the particular case, you say, does it go on in space or does it go on in time? The answer from the Big Bang is that the universe has a beginning. And so the deeper answer to why does it get dark at night, the answer is because the universe is only 13 billion years old. It had a beginning, and that we've learned why it's dark at night. And I put this here to illustrate a little bit of Olber's paradox, which is, imagine yourself in a forest. Instead of stars, we're going to be looking at trees and more trees in the distance. And you see here in this particular rendition that a lot of the trees overlap. Initially, ultimately, you will be looking at solid wood if the forest is big enough. You can see some clear sky over there at the right. This is a little tiny stand of trees. It's not that big. And so it is. And that's the same thing, is that, if the universe were infinite, ultimately, everywhere you look, you would see the surface of a star. So that tells us right now that the question, why is it dark at night, is actually interesting. It tells us something about the universe. It tells us something profound. The universe has finite age. And that's pretty good. And actually, I'm afraid that what I'm going to tell you further may be a bit of a come down from that, because we know it's dark. We know why it's dark. And we're going to ask instead, how dark is it? It's dark, but how subtly dark is it? And can we learn something from that? And so let's look at this incredible image. At first glance, this may not look like much. It's a black image with lots of dots of color on it and speckles and what have you. It is the deepest image ever taken with anything, the Hubble Space Telescope. You want to take a long exposure with your camera, you open the shutter for a while and you let the light build up. This is what you get if you take the Hubble Space Telescope and you let the light build up for 11 days. 11 days of orbiting around the Earth, taking one picture after the other, after the other, after the other, and adding them all together. And what you're seeing here are galaxies, and everything there is a galaxy. I showed you the image in the center of the Milky Way galaxy of billions of suns. Well, this is an image looking at that shows the universe has billions or almost trillions of galaxies. Everything here is a galaxy. Many of them are bigger than our own galaxy. And critically, we're looking back in time, because light takes a long time to get to us. It's called the redshift. It tells us how far away things are. The universe is expanding. The further away things are, the faster they're going, the further away. And so we measure the speed that they're receding from us. That tells us how far away they are. And they're so far away that the look back time, as we call it, is significant. The age of the universe is about 13.6 billion years. The Earth is only 4.6 billion years. Most of what we're seeing here, the light came to us from the time before the Earth was made. And let's step into this a little bit. I have a movie here. This is actually made by Frank Summers, who gave that wonderful introduction. And we're going to take the ultra deep field, and we're going to take the redshifts, and we're going to turn them into distances, and then we're going to fly into it. And so you're going deeper into this, and you're going back in time, back before the Earth was made. And ultimately, because it's what we see in this picture, we look back in time, we can see when galaxies were being made. And that's what we've learned by looking at pictures of this. But what I want you to look at in this picture is the emptiness of space as the galaxies go by. It's actually very clean. You might expect little galaxies to be next to big galaxies, or pieces of galaxies have come off in their collisions and interactions with each other, and that's true. And as powerful as the Hubble Space Telescope is, it cannot see infinitely deep. When you look back in time, we run out of galaxies. They're redshifted too far to see, and a lot of them haven't been made yet. And this region is what the James Webb Space Telescope is going to do. It's going to look even further back in time, earlier in the creation of the universe, than we could even do with the Hubble and the ultra deep field. But it's all counting galaxies. And even with the most powerful instrument, you ultimately run out of photons. And so the question is, how much light are we getting from everything? That we can add up, because maybe a galaxy is not bright enough, or it's too far away, or it's too small to make a point that the Hubble can see, but its light is still there. It'll make a fog. And so we ask, in a picture like the ultra deep field, how deep or how black is it between the galaxies? Because that will tell us what we're missing. And there's a little trick here. The Hubble isn't any good at that. The James Webb Space Telescope will be no good at that. And the reason is because the Hubble orbits the Earth. It's in the inner solar system. And the James Webb Telescope will be out a little further than the moon, but it's still going to be close to the Earth. And being caught in the inner solar system, it's vulnerable to a lot of the dust that the sun lights up. So there's a fog, this is the dense city, as it were, and we've got this bright sun, and it's lighting up all this dust from the asteroid that's grinding into each other, and it fogs, ultimately, the images that we look at with the Hubble Space Telescope. So if I measured how bright that black is, actually it would be very, very bright. It'd be much brighter than what we could understand, and the reason is because that's just the light from dust in the inner solar system. It's a false signal. And so that's why we're asking how dark it is, because we would like, to look between the galaxies and add up over the history of the universe how much light is coming from everything that made up light, but the dust is blocking us out. It's just the glow is too bright. We have to get away from that. And so the solution, which I will talk about at length, is to use New Horizons, which is at the edge of the solar system. But it's an interesting question. Is there something unexpected? What is the background? And we know that the universe actually has backgrounds. And this is a full sky image. So it looks funny if you've seen pictures, of the globe that show all the nations together, all the continents, everything. That's the same kind of projection. This, though, is the background to the universe that was very young. This is not in light that we look at. This is in microwaves. If you've heard about the microwave background, this was discovered in the 60s by two scientists working for Bell Labs, Penzias and Wilson, who found static in their communication antenna that they couldn't understand. And being very dutiful, because they wanted to have great microwave communications with their satellites, they tracked down the source of noise, and it turned out to be coming from the universe itself. And it is a revolutionary discovery. It is why we believe in the Big Bang, because the Big Bang predicted this. And the old theories went by the wayside when we started seeing the microwave background. And so we study this for the early history of the universe. And what you're looking at is a map made with the Planck satellite. And you see the colors. It's measuring temperature of the early universe. And, or as we see it now, redshifted. And red is a little hot, blue is cold. It's fractions of a degree, actually about 1,000th of a degree, what you're seeing here. But where it's concentrated, where it's a little bit bumpy, that's where matter is going to gather as the universe ages and turns into the galaxy clusters. The empty regions, which are dark, will expand and become even more empty. And this is the start of the large-scale structure of the universe. And we get that by looking at the microwave background. So what kind of other backgrounds are there? Well, we know that there's an X-ray background. We know there's an infrared background. How about an ordinary light? Astronomers have a little confusing term for it. We call it the optical background. But we want to ask, is there a background between the galaxies, which we're not aware of? And, if we get away from the inner solar system where, the sunlit dust, fogs us out, do we see something or we discover something interesting? And so a theme that I'm going to play throughout the rest of this talk is how black is black, how dark is dark. And the thing is, we are used to seeing light coming from dark or black things. And so I put up this picture here. This is a picture in front of our house in Tucson, Arizona. That's Beatrice Muller, my wife, who's a fellow astronomer. And we've been living in this house for 25 years. And the street in front was pretty old and decrepit and beat up and potholed. And we were very excited, our excitement being at home with the pandemic, you look for stuff like this. They decided after all this time to repave the street. And you've seen, how black fresh asphalt is. And it's really striking here. The old asphalt you can see in the lower right corner. And here's this jet black strip. It's very, very black. A little bit later, when they paved the other side, I went out on the fresh asphalt, and there was, the stuff on the left, which had gotten a bit scuffed up over a week, but then they paved the right part, and that was black asphalt, as jet black, as you saw in the previous picture. But, it was in bright sunlight, and I decided to take a picture of it, and you see the shadow I made. That's even darker still. And so, yes, that asphalt was really black, but when you actually cast a shadow on it, you can see, well, no, there's actually still quite a bit of light coming from it. And if you look at my shadow, though, you can see that there's little speckles, and that's where the sunlight, even the stuff, not the sunlight because I'm shading that, but all the light from the sky is actually lighting up the bright little pebbles and other things in it. So you can see there's even light coming from the shadow. In fact, it's very surprising you see something that's completely dark. And that's why I put this next picture of something that I just think is fascinating. There's a paint you can buy called Vanta Black. Vanta Black reflects only 1% of 1%, or 1/10,000th of the light that hits it. And you're looking at two identical busts. The one on the left in brass, there is the same thing on the right. It's just been painted with Vanta Black. And it's not a piece of construction paper. It's not flat. It is as 3D as the picture on the left, but there's no light coming from it whatsoever. And you lose any cues at all at what you're looking at. There's no shadows, there's no shading, there's absolutely nothing, just complete blackness. And we're not used to seeing things that black. And so this will come up at various times as I explain what we did, how black is black. And now I'm going to get into a little bit of what I did and what my friends and collaborators did with me. This is a team effort. This is a technical slide that I use for technical talks. And there's the fancy term for what we're looking for is the cosmic optical background. And optical is an astronomer's word for ordinary light, light that you can see with your eyes, that glass works with to bend around optics. And so we call it optic. If you use X-rays, you have to use something else to do that. Microwaves, to see that background, require different instrumentation. Here we just use lenses and mirrors, and so it's optics will work, and we call that optical light. And so we're looking for the optical background. New Horizons is at the edge of the solar system. It's 50 times right now, 50 times further away from the sun than the Earth. It's away from the sun and all the dust and everything the sun lights up. And so with New Horizons, which is leaving the solar system, is hanging out in the galaxy, we have the opportunity to look and see if we can measure something about the universe in the background with New Horizons instead of, say, the James Webb Space Telescope or the Hubble Space Telescope. So this is New Horizons. It's a beautiful little spacecraft. It was launched in 2006. This is down at Cape Canaveral shortly before it's launched. It's actually very small. The joke always is, you know, the shape and size are about right for a baby grand, and I think that's a fair description. You have a radio dish there for sending stuff back. It's wrapped in mylar to keep it insulated, and it was used to explore both Pluto and Jupiter, and it was sent out the solar system in January 2006 on this Atlas rocket. It ejected it from the Earth at the highest velocity that any spacecraft has departed the Earth. Apollo astronauts took 3 days to get out to the moon. New Horizons, you would pass the moon in 8 hours. And so we escaped the Earth. We left the solar system with it. We went past Jupiter. Jupiter, the little slingshot, and threw the New Horizons even further out into space, enabling us to get to Pluto in a reasonable amount of time. And the primary mission was exploring Pluto, which we did in July of 2015. And this was the same. We took Pluto, which was a little fuzzy dot, and we turned it into a whole new planet and world to explore. And we went further. New Year's in 2019, we looked at the Kuiper Belt object, which was even further away, 40 times further away from the sun, Arrokoth. And this is about the size of Manhattan, and is what we hope is typical of Kuiper Belt objects, none of which had been seen up close before. And we learned, just looking at these images with other things we did, we really learned quite a bit of how they're formed and how the Kuiper Belt evolved. The New Horizons is leaving us, is going deeper into space and out ultimately into the Milky Way galaxy. And you can see its trajectory here. So there is its launch down on Earth in 2006, out past Jupiter for the slingshot, Pluto, as I said, in 2015, Arrokoth, 2019. And right now, it's 50, what we call AU. AU is a little bit of a ruler that we use for measuring distance in the solar system. It's very handy. The radius of the Earth's orbit is 1 AU. So if a distance of 1 AU, that means Earth, things close to us. Jupiter is at 5, very simple numbers. Pluto is like about 33. Arrokoth was at 44. We're now at 50 AU, getting further away. But space is very, very dark. And that space is absolutely dark where New Horizons is going. I would like to introduce the team. The work that I'm talking about here was done with the New Horizons team. I have to say this is the finest group I've ever worked with. There's a science fiction show that some of you may have seen at various times in the title, as they narrate it, is the statement, to go boldly where no one has gone before, to explore strange new worlds. And this group really did that. They explored Pluto, they explored Arrokoth. We're looking for for a third place to go. And they made it work. And it has been my pleasure to work with this group of people over the last 6 years. I should introduce a few of them. The PI there is Alan Stern, who is third from left in the center. He is at SWRI Southwest Research in Boulder, Colorado. To his right is Hal Weaver, the deputy PI, who is at Applied Physics Laboratory in Maryland. It's operated by Johns Hopkins University, so it's APL-JHU, we call it for short. And that's where this picture is taken, where the camera is operated out of. And then there's a left Glenn Fountain, who was the project manager. And then the incredible Alice Bowman, who's the chief engineer in our version of Scotty, if I carry the Star Trek metaphor a little bit further, who knows every bit and piece of how New Horizons works and saved the day, actually, for the Pluto encounter when we had a little bit of a difficulty with the spacecraft. And then back of 100 people, and I've been my pleasure to know most of these people and what they've done, and they've been very dedicated to getting the best out of the mission. I also want to introduce my friend and long collaborator, Mark Postman, who is not on the team, but is an expert with the populations of galaxies and universe. And I brought Mark in to help us out. Mark, being curious about everything, helped out for more than populations of galaxies, and it was a key player in the work I'm about to show you. So we're going to measure how dark space is with New Horizons. The camera we're going to use is called LORRI, Long Range Reconnaissance Imager, LORRI, New Horizons. This is a picture of it. It's out the back side of the spacecraft. Actually, it was closed on that first picture I showed you, but I could have pointed out the port. If you look in there, and I'll move my cursor around, the primary mirror here, it's a small telescope. It's about 8 inches in diameter. Some of you watching probably have telescopes that big or larger. So it's a small amateur size reflective telescope. And this is just reflecting the back wall. That's a sort of standard mirror. This is the secondary, the light hits or focuses here, bounces back, goes down this black tube, and then into the instrument itself where it's recorded. It's a CCD, a small CCD compared to CCDs, only 1K by 1K, smaller than what you have in your typical camera. I can't resist pointing out something though, because this will come up, and this is more to deal with how black is black. You see that the camera has these little baffles in it to prevent scattered light, but also notice that it's not perfectly black. This one you can see is a little gray, and this one's deeper in. You can still see it. Here's one, the third one in, you can see it. So there's still some light getting around from these, and they'll come up in an interesting way. And so to measure the darkness of space, we're going to look out into our galaxy. And this is a full sky image of the Milky Way galaxy. It was taken with data from the Gaia satellite operated by the European Space Agency. And down here again, you can see the little Magellanic Clouds, or satellite galaxies. And you can see a little bit of a difficulty. You want to measure the background light from the universe, but this big old galaxy's in the way. You got this plane here. We're not going to look here. There's the bulge, the black hole that the Event Horizon Telescope imaged is right there, smack in the middle. So it's not going to be good to look here. And you can look at this and say, well, how about there? Well, it's still bright. You can see it fades away as you get, towards the poles. But we're in the disk. There's no place that we can go where there aren't any stars. There's a lot of stars in the sky, even when you look away from the Milky Way galaxy. And you can see that here again, right here it's very dark, but it's not perfectly black. So even at what we call the galaxy poles, so let's say this is the equator, this is the North Pole and South Galactic Pole, and we even have a system of galactic latitude that we use. It's our own little coordinate system for, bopping around the galaxy. We have galactic longitude, galactic latitude, here are the poles. So we want to be far away from the plane of the galaxy. We're going to look up somewhere here where the star is least thinner than everywhere else. And, we will see the distant universe, so there's no question about that. We have some other stuff to worry about, and this is another view of the galaxy taken in another wavelength. This is an infrared image of the Milky Way galaxy made with the Japanese Akari satellite. And you can see the plane of the galaxy. This is the same coordinate. There's all, where the stars are. There's the black hole in the center again. But gosh, look at what we're looking through. It's kind of cottony and fluffy up here. And it may look like, if you use your imagination a little bit, like a little cirrus in the daytime sky, when the storm is coming in, and the next day, so you see cirrus clouding up the clear sky. And in fact, we call this imaginatively infrared cirrus, because we're looking at the actual heat radiation coming off the dust. It's not lit up by reflecting light. It's actually, at 100 microns, you can actually see the dust directly just by the warmth that it gives off. But it's everywhere. It doesn't absorb a lot of light, but it does scatter light from the Milky Way, and this is something we have to think about. But here, though, is an illustration of the problem I started talking about. Notice this band that cuts across the galaxy like this. Well, what's that all about? Okay. Well, in a different coordinate system, that's the plane of our solar system. We've made this projection for the galaxy, and so that's why it turns into an S, because our solar system cuts at an angle about 66 degrees to the Milky Way. And this is what's called zodiacal light. It's called zodiacal because the plane of our solar system defines the zodiac constellations. And if you look anywhere out in the plane, you'll see that's where the zodiac constellations are. And the dust in our solar system is very concentrated around that. The sun lights it up. In this case here, the heat from the dust is visible, and this is the band of zodiacal light that completely bedevils your ability in the inner solar system to look to distant universe. And it's very concentrated here, but even at, now we're going to call it the ecliptic poles, because the ecliptic, that's our solar system, it has its own poles, north and south. And even over here, you can't see it in this map, but there's still dust there. And that's because the Earth is in the plane of the solar system. It defines the plane of the solar system. There's dust all around us. And even if I look off of the zodiac, I still get zodiacal light. And so there's a background from dust no matter where you look. And this is something you can see yourself. Again, go to a faint, away from the city to look for the Milky Way. I can go to outside the city and I can see, when the right time of year, zodiacal light. And that, is a bright glow around the zodiac. And it's fascinating. I've seen it only a few times in my life. When I've seen it, it's been incredibly clear. It's very striking. You have to be in a dark place to see it, but it's very striking when you see. Typically, I think, actually, this is a good time of year, October or March are a good time to see it. But that is, in this case, in again, the visible light, this is the dust scattering light from the sun. It's very bright. You wouldn't look for faint galaxies, looking right through zodiacal light, but it is there at some level of the whole sky. And this now is more of a technical diagram, and I won't get into it. This little cute picture here, that's a map of dust density in the solar system looking down on it. There you see these AU again. Heliocentric distance, that fancy word for distance from the sun. Pluto's about 30, Jupiter is like 5. So right here, Mercury, Venus, Mars, Jupiter all crammed into this first tick mark. But look at what happens if you're in the plane. The strength of the zodiacal light drops by a factor of almost 10,000 by the time I get out here to 50 AU. Off the plane, it's still a substantial drop going out here. And this is where New Horizons is. And that's why we want to use New Horizons for this, because it's clean out there. We do not have zodiacal light bothering us. So where do we look? This is another infrared map. It's taken by, in this case, the old IRAS satellite, which flew in the 80s. And, again, you don't want to look, where the Sirius is strong and scattering light from the galaxies. So you do want to look at the poles. We didn't, for this work I'm describing, we actually didn't use New Horizons directly. As it turns out, for just calibration purposes, looking at distant asteroids and whatnot, New Horizons had a lot of observations over the sky. We keep them in an archive for future scientific use. In this case, we searched through the archive and said, oh, well, there's some of these far away from the galaxy and some of the exposures are deep. These actually would be good for trying to find the optical background of the universe. And so this is what we started with. And there were 7 fields that we were able to identify, which were suitable for doing this measurement. And so what do you see when you looked at these images? This is what they might look like. It really doesn't look like much, and I deliberately distorted these for a particular reason. I'm showing you the 7 fields that we looked at as if they were seen with Space Telescope, as dark as Space Telescope could get. And I set this up to contrast with what we're going to see with New Horizons, and this is this. It turns out that pick the darkest sky the Space Telescope can see, and you look at it with New Horizons, it's right off the bat, over 10 times darker. And as good as Space Telescope is, it can find incredibly faint galaxies, incredibly faint stars, but it does through a sky which is still relatively bright, and that's the brightness at the Space Telescope. This is what we're looking at. And so, what do I want to do? Or what do we want to do? And the answer is, okay, it looks pretty simple. And if I gave you these images, you could try to do it yourself. Let's say, well, okay, I've got these images. Yeah, there's lots of stars in even these images, because again, you saw that image, there's stars everywhere. There's some faint galaxies that have to go, but they're not incredibly crowded. So let's look around and make a measurement between the stars. Let's block the stars out and measure things in between, and we'll make a measurement. And that's the measurement of how bright the background sky is. But that leads to a lot of work, which I'm going to talk to you about, because there's other things that come in besides this background that we're looking for. And that's what we had to be very careful about. One of the first questions is, are you fooling yourself in some way that you don't know about? Nighttime is something in a way that doesn't really exist in the universe, even where it's dark. Being at night is really in the shadow of the sun. If you're on a spacecraft, even 50 AU out, you're still in bright sunlight. The sun is surprisingly bright, even at as far as we've gone. I mean, it lit up Pluto for us, lit up Arrokoth, quite easily, and so it lights up the spacecraft as well. And so the first question was, we had to make sure that we were looking, fully away from the sun with these images that we found in the archive. Well, we selected them that, they were at least angularly far away from the sun. But we were concerned, was there light that was getting in anyway? So here is what the spacecraft looks like, just lit up in sunlight. And there's Laurie there. It's its aperture. It has a door which opens. It opens only once. It's blown open and it stays open for the whole mission. But wait, what are these things here? Gee, okay, well, these help us with navigation. These are our star trackers, which we get the position of the spacecraft from, and they kind of stick out a little bit. Oh gosh, are they lit up by the sun? And this is, by the way, why you work with a good team. There was a team member named Mark Bowie who is incredibly clever with anything with the spacecraft, and I didn't know what to talk to him about, except I asked Mark, tell me what I don't know. And he said, you should think about the spacecraft. And then I talked to a planetary astronomer who was an artist named Dan Durda, who was not on the team, but close to the team. And he had this model which rendered New Horizons just because he liked putting it in images. And we used that to do the geometry of those fields. And we said, how, when New Horizons was making those observations, was it dark enough? And so we figured out the geometry for those images. We figured out the geometry of the spacecraft. We lit it up with the sun. And here are for 5 of the fields. I said there are 7, but 2 of the fields, that have the exact same geometry. And you see, look at this. Okay, here's the sun. It's lit this up here, and there are those star trackers. Ooh, okay, they're lit up a little bit. Oh gosh, here they're lit up a lot. Oh, what's this? Oh, that's this little latch thing over here to Laurie. Oh gosh, that's in a little bit of sunlight too. And then we we measured how much light we were getting in, and we're pleased to find out that not much was getting in the camera. In fact, a trivial amount. It wasn't going to hurt us. But this is the kind of thing you have to think about. When you're measuring how dark something is, what's the light that's coming in that's bothering you that has nothing to do with that? In fact, we had a telecon once, and when we're working on this, and I remember Alice Bowman was there and Alan Stern was there, and we were killing time before it started. And I asked Alan, so are you sure that there's no navigation lights in the spacecraft? Because Alan is a pilot and is really loves thinking about spacecraft. And there's no reason to put navigation lights on New Horizons, but it would look cool all the same. And this, got laughters around the group. No, we're not going to put light bulbs to wink on and off. The Enterprise has them, but New Horizons doesn't. But it's that kind of thing you think about. What light could be there that you haven't thought about? It's going to give you a positive signal. It's going to be completely wrong because you didn't account for it. And that's what we had to do. And that's why we got this rendering software to look and see, was there something coming in? Well, we got another thing to worry about. What about starlight? We're looking at fields. You saw there are stars in the images, but what about bright stars away from? They're not in there, but they're still putting light into the camera. And we know how Laurie, the camera, responds. This is, again, another technical graph, but this is actually how it responds to sunlight. Notice this compressed scale here. So what we got there? We got 100 million there, and we got 100 millionth there. So that's 16 orders of magnitude, and the light goes with sort of like 14 of those. And I had to use a new word, quadrillion. You've got million, billion, trillion, and then 1,000 trillions is a quadrillion. And so sunlight coming straight into the camera, if we pointed the camera at the sun, which by the way would ruin it, but going all the way out to 90 degrees, here the sunlight intensity drops by a quadrillion. But if you point near the sun, whoops, not ready for that one yet, you still see sunlight coming in very faintly. And the sky is actually pretty bright, unless you're actually in the New Horizons shadow, because the sunlight is hitting directly into the Laurie aperture and it's scattering around. Remember that baffle was not, completely perfect. You can still see it, which means it's scattering light. And if that can scatter sunlight, well, a bright star, is going to get in the same way. It's not going to be that bright, but you better think about it, okay, because you're looking for something very faint. And so we took every catalog we could get that help us out, and we were going from very bright stars to very faint stars. This is something that Mark and I worked on very, very closely. It took us 3 catalogs. We needed a catalog of bright stars that you could see with your own eye, and then we needed a catalog you could see with small telescopes, and that was Hipparchus, and then we needed Gaia to get us to the faintest stars that Laurie could see. And this is again more technical, the diagram, but this is what we had to worry about. So here is the field of view of Laurie, another logarithmic scale, 10th of a degree, 1 degree, 10 degrees. So this is compressed. But we said, what star is putting what into Laurie? This is to be in the camera, you have to be inside this thing. But what's this over here? Here is a star, and the brightness 0 to 5. Those are stars you can see with your eye. Binoculars out to 7, small telescopes out to 14, big telescopes out to 20 if you look in them. So bright, faint. I don't know what this star is, but it has a name, and the astronomer will almost certainly know it by name, and it's 10 degrees away. Not even close to the camera, but gosh, we know from our little scale here that there's a lot of light going to come from that. Here is something that's 3rd magnitude. These are called magnitudes. It's 3. That's putting in a lot of light into this. And so we had to go over the whole sky, integrate up with all these star catalogs, and ask the question, how much scattered light were we getting into? Because again, if we didn't think about that, we say, oh, look at all that light we're getting. And it's completely wrong because we didn't account for this. Now there's something else we have to think about. So here we're back at the ultra deep field, and these are these beautiful galaxies that took Hubble a week to detect and pick up. Well, they're going to be in our field too. And we have a small telescope and we won't see them like Hubble will, but they're going to put in light all the same. So we better account for how much galaxy light's in there. So that's something else we had to worry about. And this is something, again, that Mark and I worked on. This is excessively technical, and so excuse me for showing this, but this is a scientific way of presenting what we know about the populations of galaxies in the universe. You see 6 little plots. Well, those are different colors. If you looked in the ultraviolet light, blue light, V band, that's called visible band. That's what the eye is most sensitive to. It's kind of green. Red, infrared, and then a little bit further infrared. So these are different colors. And you see there's a steep curve, and this is faint this way, and this is number this way. So here we go from this way. Okay, galaxies in green light, not many bright ones, lots and lots, oops, you can see my cursor, lots and lots of faint ones, and this is true for all of them. There's another curve. Stars do the same thing, but they're easier to get rid of. It turns out when you get past a certain faintness, it's galaxies that you see, not stars. There aren't as many of them. But this is something else that we had to account for, is how much galaxy light were we getting. So here's the answer that we were going for. And so we had 7 fields, so we looked at, and here are measurements from 7 fields. And we got a solid signal in all the fields. You can see there are error bars there. That's pretty precise. Look at that. And I won't tell you what the units are unless you know that you're good and you know what nanowatts per meter squared per steradian is. There's probably some of you who don't know what that is, and I won't explain it. I hope to explain it better than that. But just take the number. And so whatever this mysterious number is, take like 35. We see 35 of this thing, and you know that doesn't matter what we call it. If we're using Hubble Space Telescope, which is all fogged out compared to this, this would be up at 300 or 1,000, okay? So what we're seeing is really dark. But that's just a raw signal, and that's what we measured from that slide several times back. I just showed you the pictures, and this is what I get, when we just measured off the pictures. So is there something here, and we need to look at the budget. What could be making this signal up here? Is it something interesting, or is it something obvious, or is it something stupid? So I was just talking about galaxies. So let's talk about galaxies. Oop, wrong cursor. Let's go back so you see. Yeah, so here we go. So I said there are faint galaxies that are in our field that we can't see. How much light did they put in? That's the blue. So, okay, and we compared to lots of different people who work with galaxy counts, and that number is pretty good. It's known from the work with Hubble. It's going to be refined with James Webb Space Telescope when that launches. And you see there's a big gap between the light contributed by galaxies and what we actually measure. That's huge. Well, okay, faint stars, we got some of that. And that's red. And as I said, there aren't as many stars in our fields as galaxies. So, that's not a big correction. But I went on and on about scattered starlight, light from stars off away from the camera coming in. It's like lens flare, by the way. You see this when the sun, isn't in the picture, but it's still flaring in. Well, that contributes to this, and that's our scattered starlight. These are bright stars that we're not looking at. They're not getting in the camera, but they're off, and they're bouncing around those baffles, and they're still putting light into the images. And so they're contributing what you're seeing here, and that's the gold. And I also talked about that infrared cirrus around the galaxy. That stuff is up there, and it's bouncing in light from other stars in the galaxy, and it's putting in a little fog in the images. And that's this there. And we don't really know it as well as we'd like. There's two different research papers that said what it is, and one's in dark green. We like that better because it's smaller, so we made that more obvious. But there's the one in faint pale green, and it's somewhere between that. And so this is what we're left with. And this is interesting. This now is all the light that we think we can account for. We think we've done our homework. We think that we have seen what's there, and we don't make it up to our actual measurements. There's a difference here. There's a gap. There is extra signal that's unaccounted for. Its origin and purpose still a total mystery. But whatever it is, it's as big as the light from galaxies. So what we're finding here is that accounting for the faint galaxies, we still have something just as important left over. So we'll get into a little bit of how much light is this, and that's something I do want to explain to you. So if you don't like this unit over here, which is nanowatts per square meter per steradian, I have what I'm hoping is a better unit that I'd like to introduce in common usage in the astronomical world, and that's the fridge. So I showed you the outside of my house. And if you walked into our kitchen and opened up the refrigerator, it'd probably look like your refrigerator. And this is the middle of the night. So I think, all of us who are bad and raid refrigerators in the middle of the night, what it looks like. And you can picture being in the black house and, nothing else on but the light from the refrigerator. You know how bright that is. And you can see, it doesn't really even light up the kitchen that much. And now let's take one step further, okay? Let's not talk about my kitchen. Let's talk about the neighbor's kitchen. And so let's go out to the country, away from the city, and pick a clear, brilliant, moonless night. And here, that's, I should say, not our neighbor's cabin, but let's say there in the foreground there in the right, that's your cabin. It's where you're living. And there you can see already that, you've got more light there coming out than is coming out of your refrigerator. And so, you go to bed and it's the middle of the night, you turn off all the lights and you've left your curtains open so you can see, you would see the moonlight when it comes in. Somebody drives the road along and swings the light across the lake, you can probably see their lights. So here's your neighbor there, and they're a kilometer away from you. And your neighbor goes into their kitchen in the middle of the night and opens their refrigerator, and it lights up their kitchen, and the light spills out of the window and gets into your windows over here. That's how bright this unknown radiation is. Actually, that's how bright, if you add up all the galaxies in the universe and coming into your kitchen, that's how bright it is. It's very, very faint. You might notice the moon, but you probably won't be woken up in the middle of the night by your neighbor raiding his refrigerator a kilometer away in the lake. But you can picture this. You know, if you look directly at it, you can see it. It's, you know, in that sense, it's interesting. It's, I think, a way of feeling the light. And I'm going to give you another way, and that's actually how I found this picture. For those of you who know your constellations, and you should all know your constellations, you can see a bit of Orion here. There is Betelgeuse and Rigel, and the belt of Orion, and its sword underneath where the Orion Nebula is and star formation is taking place. And Orion is a winter constellation, and winter is on its way. And if you get up, you know, late now, you can see Orion coming up, and it'll be spectacular across the skies, you know, as we go into winter. Over here is the brightest star in the sky, and that's Sirius. And you've heard, you know, Sirius Black, that's the one he's named after. And it turns out that if you don't like my refrigerator units, then I'm going to give you Sirius. The light coming from Sirius in the night sky is equal to this unknown component lighting up the landscape. And so if you can see a moonrise with lighting up your window in the middle of the night, you probably, you know, won't be woken up when Sirius clears the horizon, but that's how much light makes this unknown component that we're talking about. So a little bit on what is it. So we'll go to the next slide. And I just want to show you where this is quickly, another scientific slide. This is our measurement here. And the thing without, you know, zodiacal light, we have much smaller error bars than has ever been done before. People have tried this over and over again, but they get very large error bars, and even just the detection of the background is not particularly significant with these measurements. We have a very good detection of the background, and we take it off, we have, you know, an okay detection of the unknown part. So I don't know if this will work with you, but I will try to talk your way around it. So the best guess, what are we looking at? You know, have we counted our galaxies right? You know, that's something which is frontier research, adding up all the galaxies in the universe. The yellow line is a range of plus or minus where we think it is, that's the yellow. And here's our measurements up here, and that's why we think there's something unknown. But even the Hubble Space Telescope can't see everything. And we have to extrapolate those counts that I showed you to what you can't see. And that's what this is. And if, and there's a black line, if we extrapolate by just how it looks for the brighter galaxies, you know, we extrapolate to the faintest possible galaxies, and it doesn't change, you know, then we can't explain it. But let's say all of a sudden these faint galaxies, you can see there's more than you expect from your extrapolation. Maybe, you know, it comes up and there's, you know, gobs and gobs of faint galaxies. And so that's called a steep slope, that there's more than you expect. And so if there is an unknown population of faint galaxies, that could explain the light that we see. And so this is the exercise. We think this is useful because it pushes against what we understand as the population of faint galaxies. It gives us something to check. That is, add up all the light, add up the galaxies you can't see. If there's a difference, it means something is new. Either it's galaxies you can't see, or, you know, something that you haven't seen. And I say the bet is that what we are seeing is just parts of galaxies that have come off or haven't been counted yet. But it's something unknown, and we leave open the possibility that it's something not to do with galaxies, something unexpected, perhaps something even closer than the distant universe, which will be a surprise to us. And so with that, I should probably wisely fade to black. But as they say in the old advertisements, you know, but wait, there's more. And let's see if I can do this. I was about to leave my talk, which would be bad. Oh, now I see what I need to do. I need to stop sharing. I'm going to share something else. So what I told you was that we used observations that were taken with New Horizons for something else, so an archive. We actually didn't point to spacecraft that did this. We used data that had already been taken. And as a result, we couldn't be picky about what we had. And I showed you that we had to take care of scattered light from other stars, and we had to account for light coming from our own, scattering off the cirrus around our galaxy. But if we can pick and choose, if we can plan the observations in advance, we can find darker places to look, and we can make our error bars smaller to make it unequivocal that we've seen something unknown. And so the first thing to do is to test that possibility. And one thing that we were able to do, because we were looking at how well the spacecraft performs for future research ideas, this year we picked a field that was extremely dark. It should be much, much darker than anything where we've seen before. It should have no contribution from scattered light off the Milky Way at all, and have much less scattered light than we saw. We developed, or I should say, the whole team you saw there with the engineers working, developed this command sequences for the spacecraft. They were verified, tested to make sure they'd be safe, and lots of planning going into that. They were uploaded into the spacecraft in the middle of September. And this is done every few weeks for the spacecraft to run commands. A Friday ago, our observations were taken on the spacecraft. And they sit in the image store waiting till they're coming down. And so tonight, I'm looking here at this wonderful website you can go to. We get data from everything off the Earth, planets and the moon with Deep Space Network. It goes back to the times of Apollo. It's how we could see the astronauts walking on the moon. It's how we get pictures back from Pluto. It's how we got pictures back from Mars and Mercury and Venus. All the planets come back with the Deep Space Network. And these passes are programmed very carefully to get data from the spacecraft. And if you look over here, you can see Goldstone. That's one of 3 stations spanning the world. There are 3 stations, one in Madrid, one in Goldstone, one in Canberra. This is the biggest, this is Goldstone. And you look here, the telemetry is active. Data is going up the spacecraft, data is coming down from the spacecraft. And here's the acronym, NHPC. That's the DSN code for the New Horizons spacecraft. And so right now, the large 70-meter dish at Goldstone, which is in Mojave, is talking to the spacecraft and it's getting data from the spacecraft. And I happen to know that's our data that we took for a trial. So as I've been talking to you, New Horizons light travel time is 7 hours. That our data from these images is beaming across the solar system down to Earth through the DSN. And so after I'm done talking to you, I can get rid of the Zoom and other things, and I can bring it up and I can see what we got. And with that, I think I'm going to stop talking.
All right. Thank you, Todd. That was a wonderful talking with a great little finish in that, there will be more because the data's coming down right now.
Wait, there's more. Yes. Still not satisfied? Yes.
I will have to say, I sort of took a riff off of one of the comments on the chat on YouTube. And it turns out that you joined the New Horizons team and you went over to the dark side.
Well, I can tell you, so I can't resist telling you this. So I did this, and a paper that just got accepted was using the light of Charon to light up the dark side of Pluto. And so one of the persons on the team has called me Dr. Dark. I kind of like that. Dr. Dark. I don't know. Maybe I get a license plate, printed that up.
Okay. So one of the questions from our audience was about darkness and the expansion of the universe. That is the universe also dark due to the expansion of the universe?
Yeah, and that in fact is correct. That's a very good question, and it's easy to answer. I mean, there's part of the darkness is the fact that it's taken so long for light to get us, even from the start, that would limit the brightness. But the fact that, distant galaxies are redshifted, that's why we have the James Webb Telescope. The forming galaxies right at the start of the universe, we can't see with an ordinary telescope. Their light is shifted into the infrared. So yeah, that is also part of the factor for why, why we can only
Cool.
see so far, see so much.
All right. Well, I'm sure there were other questions that I didn't have a chance to write down, but Grant Justice has been following the chat more closely than I. Grant, why don't you turn on your video and tell us what questions you found in the YouTube chat?
Absolutely. All right. So let's get us started off here. And this is one that I feel like a lot of people think but don't necessarily ask, kind of what we were talking about
The
before.
question that cannot be asked. Yes, go ahead.
Yes. So, and this is one of the big things with James Webb, and especially with space and darkness as well, is when you're looking for things that are so far away, things that have such small photonic signatures, you have to collect so much light and be able to see it. What exactly is it that you're looking for there? Not necessarily what heavenly body, but what is it that you're detecting?
Well, it's with, not quite sure. There's a technical thing. Let me give you the technical answer.
Bring it on.
It is light. It's for optical light. We have a CCD, and those were once exotic devices. I did my thesis with one of the first CCDs around, but you probably have two of them. You can't see that with my background coming in, but you have two of them with you in your phone, right? Backside, front side, and that's the CCD, and the sensors are not that different. The James Webb Telescope sees the infrared, so you need a different kind, but it's a solid state thing. Photon comes in, makes an electron. Electron, builds up for a bit, and then after a while, you quote, read it out, you count them, and that gets turned into a number. And so everything is, if you want, light being turned into numbers, and that's what's coming down with the Deep Space Network right now. The Deep Space Network is sending us numbers, saying how bright is it in this pixel, how bright is it in that pixel, and that's what the data look like.
Okay. Kind of building on that as well, what efforts were previously made to measure blackness? Like what kind of instrumentation would you use previously before we had infrared and a lot of the more advanced stuff we have now?
Well, you use some of the advanced stuff. People have tried this with the Hubble Space Telescope, and this is the thing. I mean, just because something's hard doesn't mean you don't try it. And in fact, I'm being a little cavalier, is you always try hard stuff. It's always at the frontier. And so this question has been around for decades, and people have tried a different way. It's hard from the Earth because the Earth's atmosphere puts out yet more glow, that gets in the way. But work was done, oh gosh, I'm trying to remember when this was, in the late 90s with the Hubble Space Telescope. And, it was bothered by zodiacal light, but there are clever people say, well, I think it looks like this, and I can take it out if it has this distribution. And they're completely right, they can do that. But it puts noise in, and there's uncertainties. And the thing that's a little bit hard for people to put their head around is we often are not so much interested in the measurement, but the errors. I don't really care what the number is, but I do care if the errors are small. And so people made the measurements, but the errors were just very big. And they were honest about the errors. And so we tried this. There's a Japanese probe rocket called Cyber, which is for this thing. It's suborbital, and so they had to take care of zodiacal light as well, and they had ways of doing that. But again, you get large errors. And so a lot of the measurements, and I had that in the figures, said, yeah, maybe something's there, but the errors weren't, small enough that you could be completely sure about that. In our case, we didn't have
zodiacal light was always the major fact that you couldn't gauge perfectly.
You couldn't get around that. And so we're not clever, we're actually lazy, we right? We're so lazy, we put the spacecraft that is this whole solar system, but it has no zodiacal light, so I don't have to do the fancy stuff. I have to worry about other things, but I don't have to worry about that. And so that makes that part easy.
Okay.
Okay.
All right. Yeah.
Is that okay?
It's basically if you produce your background noise by
I'm
a
sorry,
factor
I-
of 10
I-
by a
I've-
factor of 10, it's that's quote quote easy, and now you have to worry about all the really small things.
You looked a little stunned there, Frank. That's why I was like, oh my God.
Oh no, I was just sort of expecting Grant to jump in, and
Okay. Okay.
we missed our
Grant,
cues.
Grant,
We did.
Jump in. Jump in.
I was too busy listening. I was waiting
All
for
right.
the next sentence to start.
Okay,
All right. Here we go.
I won't
Oh.
let you start your sentence. I'm going to give you more, but go ahead.
Bring it on.
Right.
One of our returning guys. What's the darkest place in the universe that you know of or have observed?
Well, the darkest place. You know, it's funny if you just, you know, the old dark rooms, right? If you just went in, you know, to develop film, and you seal up everything. That's probably as dark as anything. No light whatsoever. But no, you know, that's not that's I can't answer that question very well, because what I said so far is, you know, I just took what was off the spacecraft. What I would say is those images were the darkest sky ever seen by any spacecraft. So I would say what you have seen there is the darkest things they've looked at. And
So-
you know, the data I'm getting down right now, that while we're talking, that may be darker yet. That would actually be a record breaker.
So there was a little speculation about what about a black hole? Would that be an absolute dark, like reference calibration source or something? Not that New Horizons could see a black hole, but you know.
Well, boy, I'll tell you, I wouldn't want to do that because right, you say, well, we need a black hole. Well, point's not going to be, oh, let's get close enough to the black hole, so it's
Exactly.
spread out a little bit. Yeah, so it fills the sky like the moon or something like that. No, you wouldn't want to be anywhere near that. So
And plus, you know, how could you avoid the photon sphere around the black hole, right?
no, I mean, there's things falling into black holes giving off light, and so even black holes, you know, well, yes, nothing can come up. A lot goes in when a lot of stuff goes in.
There's so much light around the black hole
around the black
that
hole
it would contaminate all your
that-
observations.
Exactly. I mean, it's a great idea. It's a
I
clever
thought it was a
question.
very inventive idea.
It's a clever
to
question,
appear up in the chat.
but it doesn't work.
Okay. Well, I actually
right.
have a question myself. Did you sit there and do the calculation that 25 watt light bulb in a refrigerator is at 1 kilometer is equal to the light from Sirius at what Sirius is 8.8 to light years away?
No, I just looked it up on the web. You know, you have these every. No, sorry. Google light bulb refrigerator series. Oh yeah, somebody asked that question, you know, 5 years ago, and you can. Yes,
Absolutely.
yes. No, I did that. Because I really wanted to visualize what the light was like, and Mark Postman also did that, and we got the same answer. And yes, a refrigerator lights is 25 watts. How far do you have to put it away? It's about 1 kilometer. And it turns out I want to do it like a star, and Sirius is the same thing. So, you know, there you go. So yes, I did do that calculation myself or ourselves, and we had our math checked. And
So Sirius is one fridge of
Sirius
provides only one fridge of light. Okay.
one fridge of light. Yes. Well,
Okay.
let's make this.
I'm gonna try and work that into my next talk. Okay.
Yeah, I want the IAU to define this thing, but yes, a fridge of light is an open refrigerator a kilometer. That's the background radiation measures.
All right. Fantastic.
Anything but the metric system. We're using refrigerators of light to measure distance.
Well,
Yeah,
a kilometer is in there, but that we'll ignore that.
I know, it's just it's too
All
good.
right.
It's too good.
All right.
What else we got, Grant?
All right. So let's see. Looking through. All right. So given your field of study and the specific conditions that you use and you have to work in, where would be the ideal place for us to place either a telescope or a spacecraft for your type of observations?
Well, where New Horizons is right now is pretty ideal. That's hard to beat. You probably wouldn't send a spacecraft out for just this measurement. Now, what's interesting is that if you put, you know, the James Webb Telescope out there or the Hubble Space Telescope with a darker background, boy, they're a lot more sensitive to galaxies. It's a funny kind of thing, right? You know that the stars are there during daylight. You know, you just can't see them because the sky is too bright. Well, the zodiacal light for Hubble Space Telescope, that interferes with its ability to see the faintest galaxies, and the same thing for the James Webb Telescope. And so if you were to put them way out in the solar system, they'd be much more superb for faint galaxies. It'd be very, very nice. But the telemetry, the expense of operating at enormous distances, it makes it extremely difficult. And it's very difficult operating New Horizons. So you probably wouldn't you probably wouldn't mount a mission just for this.
So that brings up a question. We've been able to contact Voyager out to about 120 AU.
Yeah, 100.
And,
It's 120. Yeah.
And so New Horizons is at 50 AU right now,
Right,
and it's
right.
moving much faster. How many more years do we have where we can still talk to New Horizons?
Yeah, actually, it's not moving faster. It turns out that the Voyagers are given where they went.
But we always say New Horizons had the fastest move of any spacecraft that we've launched.
When we launched it, it was true.
Oh, when we launched it.
So
Okay.
you got to read the fine print. There's fine print that you didn't read.
So Voyager got the slingshots and got faster.
The slingshots, yeah. Voyager said, no, no one's going to catch me, and New Horizons didn't try to catch it. But your question is, and one of the things that's funny, New Horizons was compared to Voyager was made on the cheap, and we had a small dish, and so the answer is. We're looking to get out to 100 AU, and we may be able to make that, and that will be in the late 30s, and so that's probably about where we'll go. So where Voyagers are now, we will probably not be able to talk to New Horizons as far as the Voyagers have gotten out. We just don't have the transmitter, the dish, and the power reserves to do that.
So in the direction that New Horizons is going, it's not really going to reach the heliopause, is it? Before we won't be able to.
No, unfortunately, yeah, we should not see the heliopause before while we can still talk to it. Unfortunately,
okay, because that would be a fantastic, a wonderful verification.
It would be great, if you have somebody, we could go there. If you have some plutonium in your pocket, we could go out there and gas up the RTGs, right? Refill that. Buff it up a little bit, give it a bigger dish, then we're talking. Refuel it, by the way, while it's up there, then we could really do something. So, nobody's seriously talking about that.
All right.
I've
Grant, got 2 more questions?
I've got 2 more to finish this up, if that's okay.
2 more, let's do it.
All right. So first one off here. Is it possible that there are objects in the universe that are beyond what we can see now? And if true, well, realistically, we know that there are things that we can't see and can't observe. But is there anything that you think we will not be able to observe just based on location, based on obstruction, based on being near a black hole, radiation being pulled from? Is there anything that you think we won't be able to actually observe?
Let me answer that question a little bit differently. I think that's very hard to answer, so I'm going to answer a different question that you didn't ask.
Okay, fair.
I like that question. But I have a great answer to a different question.
It's very political of me. It's a style. Yes, I know what you asked, but I'm going to answer something else. I showed you a picture of the galaxy in the plane. And we know already that, being in the planetary galaxy makes it very difficult for us to see what's not, what we're actually blocking. And you saw there's dust in the galaxy. There are parts of the galaxy that are very difficult to see. And, you think, if you were in the center of the galaxy around all those stars, boy, you would have trouble seeing a distant universe. Astronomy would be very difficult. And so it's an interesting question to play, a parlor game, astronomers, if, I don't know, I've never been to an astronomer parlor, but if you imagine there is such a thing,
Right.
sorry.
In the late evening at a AAS meeting. Right?
Yeah, I guess that's as close as to an astronomer's parlor, yes. And there has to be some good drink involved for this. But it's, a great question is, what's wrong with where we are? What are we missing? Because you can say, boy, I'm glad I'm not at the center of the galaxy because I wouldn't know this. Or what if I was in between Andromeda our galaxy, and I couldn't get parallaxes to figure out distances. I wouldn't know what they were, Or
What if our sun was in a globular cluster, right?
Yeah,
The
exactly
whole
right.
sky would be just so bright with stars, it'd just destroy our
No,
ability.
you'd have trouble. You'd have trouble understanding what you're looking at. But there is some ways which which limit our view, and I've suggested a few of them, that we're in the plane of our galaxy. And so it's asking, what is it that we don't know? What is wrong with our vantage point that is limiting our ability to do this? It's like, the unknown unknown. Maybe some of the things we think are because there's something limiting what we can see. And that's an interesting question to say, what could that be? So if that's an okay answer to that your question.
I feel like that was
What-
reasonable.
I know. Ask the person to see if the needle goes up. Yeah, I don't know. Plausibility scale.
Frank,
right.
do you have any more before I ask the last one?
Ask the last question. I'll have a final comment.
Okay. This is one, I'm going to bring it back a little bit because we're getting a little bit into the weeds here. This is one that I've seen
The parlor
repeated
game.
several
Yes. No.
times.
Let's get out of the weeds. Sure. Yeah. Maybe you should go into the weeds. That could be just as good. But go on.
It could. Some
Yeah.
of the chat would definitely like us to go into the weeds, but just given the amount of times I've seen this repeated,
Yes.
what is it that causes galaxies to appear to be closer together or in like tighter formations the further away that we are observing them?
I'm not sure I can answer. I don't know that is so.
I've seen it repeated in the chat like 4 or 5 times. I wanted to get your input here.
I'm afraid I'm baffled because I don't understand that is so.
Yeah, the 2-point correlation function of galaxies with increasing redshift.
Well, I mean,
Yeah.
what we can say, the only thing I can say is galaxies do like the company of other galaxies. They're not spread flat or randomly. And in fact, your background right there, Frank, is perfect. That's a cluster of galaxies where the galaxies are very dense and closely associated with each other. So there is that, gravity pulls
But
galaxies.
that develops over time. It doesn't develop back. It decreases back in time.
Yeah, back in time, galaxies are, if anything, less clustered together.
Yeah.
That's how I would answer that.
Okay, solid.
Yeah. So you mentioned an astronomical parlor, and I was remembering 25 years ago when we were at the AAS that we were talking about in San Antonio.
Yes.
And Neil Tyson had a bottle of wine out.
Yes, he did.
Yes, and we were sitting around chatting and such.
I actually remember that conversation.
I remember that conversation, and I remember in particular, because you said billions tonight, a certain person doing a very interesting Carl Sagan impersonation at that astronomical parlor.
Somebody might have done that. I don't know who would have done that.
I don't know who would have done that.
Yeah,
but I was waiting for you to do the billions and billions here tonight.
Like the rising of 400 billion stars, the innumerable bounty of human existence. Yes, sorry.
Well, thank you very much. I can talk you into doing that.
All right. You better give me a bottle of wine for that.
So, thank you. Thank you so much for being here, Todd.
Okay.
Really appreciated having you.
Thank you. This is fun.
Thank you to everyone who's watching. Next public lecture series will be November 2nd. Please join us. Thank you all and have a great day.
Cheers.